Imagine a single concrete wall that controls the drinking water, the farmland, and the electricity for hundreds of millions of people downstream. It controls when the water flows, how much flows, and when it stops. This is an active construction site right now in a deep canyon on the Tibetan plateau. China is building a hydroelectric project designed to be the largest dam in human history. The water that will flow through this canyon feeds directly into India and Bangladesh. The survival of those two nations relies on this river, and their water supply depends on a single upstream choke point. By placing a concrete structure across this specific point in the river, a free-flowing natural resource becomes an engineered asset, a mechanism for direct physical control over the water's flow. To see why the location matters, we have to follow the water. The Brahmaputra River begins its life as melting glacial ice high up in the Himalayas. It starts as a relatively quiet, slow-moving river crossing the Tibetan plateau. Here, moving eastward, Tibetans call it the Yarlung Tsangpo. This map traces that eastward journey. But when the water reaches the eastern edge of the Himalayan mountains, it makes a sudden 180-degree turn to the south, heading directly toward India. As the map tilts into a 3D elevation profile, you can see what happens during that turn. The river plunges 2,000 meters downward in a very short distance, carving out the deepest canyon on Earth. The water accelerates, thundering through these sheer, rocky walls, right before it crosses the border out of Chinese territory. Geography has provided the perfect placement for a dam. Whoever commands the river at the exact moment it exits this drop dictates the flow for everyone downstream. For engineers, the combination of a massive volume of water and a severe 2,000-meter vertical drop creates the ideal physical conditions for generating electricity. Current Chinese assessments project the dam will generate 60 gigawatts of electricity. To put that in perspective, the Three Gorges Dam, currently the most powerful on the planet, maxes out at 22.5 gigawatts. The new dam is designed to nearly triple that output. Beijing points to this project as a core piece of its climate strategy, utilizing renewable hydroelectric generation to replace coal-fired power plants and reach carbon neutrality by 2060. Building in a remote, high-altitude location with vertical cliff faces requires boring tunnels through solid rock and suspending access roads. It pushes the boundaries of large-scale civil engineering, carrying an estimated price tag of $140 billion. For China, this expenditure buys a domestic energy triumph. It is infrastructure built to fuel their grid and achieve national development targets. Downstream, the math is interpreted differently. Creating a reservoir requires holding back water that would otherwise naturally flow forward. The operator controls the release mechanism. Opening the gates creates a downstream surge. Holding it back induces scarcity. Nations along the Mekong River have already recorded changes to their water flow patterns. During severe droughts, they observed upstream Chinese dams maintaining high reservoir levels, while downstream communities experienced acute water shortages. Once the Brahmaputra exits the canyon, it flows straight into India's Assam state. 50 million people here rely on this river for drinking water and irrigation. The entire local ecosystem depends on predictable seasonal flooding. The river naturally deposits nutrient-rich sediment over the land, a rhythm that has sustained rice paddies and tea plantations for thousands of years. Further south, the river merges to form the Ganges-Brahmaputra Delta in Bangladesh. You have 170 million people living on a low-lying landscape built entirely from river sediment. A sudden drop in water levels, particularly in the dry season, strips away the agricultural viability of the delta. Altering the river's flow threatens the physical foundation of these communities. The physical threat of the dam is magnified by the political reality of where it is being built. India and China share a 3,400-kilometer border, large sections of which are actively disputed. These two countries fought a direct border war in 1962. The military tension persists today. In 2020, soldiers from both sides engaged in fatal hand-to-hand combat in the Galwan Valley. And while they share a border, they do not share a binding international water treaty. There is no legal mechanism forcing comprehensive, real-time data sharing about upstream dam operations. Without legal obligations or diplomatic trust, Indian strategists are forced to evaluate the dam not as a power plant, but as a permanent lever held by a nuclear-armed rival. The calculations for both sides are about to become more desperate. Rising temperatures are causing the Himalayan glaciers to retreat, meaning the river will eventually lose its reliable year-round source of meltwater. As natural rainfall becomes less predictable and droughts more frequent, physical control over whatever water remains gains increasing strategic value. The country operating the upstream infrastructure will have the power to secure its own water needs, while hundreds of millions of people downstream are left to manage the resulting deficits. The Brahmaputra Dam occupies two realities at once. It is a massive project for generating clean energy, and it is a new strategic lever in a region already defined by competition. Every cubic meter of concrete poured into the canyon increases grid capacity, while simultaneously establishing physical control over the downstream water supply.